Hello, everyone. Thank you for joining me today. I mean, the talks so far at Hack in the Box have been, really great, and I hope that this one won't disappoint you. And during, our time today, we're gonna take a look at, Garmin smartwatches. The roadmap for today's presentation is to give a quick overview of, what Garmin is as a company and why focusing on the, fitness division. We'll do a little bit of recon regarding, the devices itself, what it includes and, what you can do with it. We'll discuss a bit more about MonkeyC, which is a Garmin custom language that they wrote, for developing third-party applications. A quick, few tips on firmware analysis, when it comes to reversing the devices. Then we'll move to a few examples of, typical vulnerabilities that we could find in the firmware, affecting the device. A quick demo exploiting one of those vulnerabilities on one of the devices that I have here. A conclusion and a few pointers to, areas of research that you might want to have a look yourself, or if you want to collaborate, I'd be happy to. So, Garmin. Garmin very quickly is a company that existed, for the past couple of decades. They haven't started necessarily in the fitness, but nowadays the main division is related to fitness and outdoor, division. So they have devices ranging from, marine GPS devices. They even have like electronic, integrated in cockpits, and also, dog tracking solution and whatnot. But today we're going to focus on that outdoor fitness division that includes, fitness watch, but also GPS and electronic bags. The Forerunner series is, a series of devices that they've, created. It exists, since 2003, and to this day there is, if I'm still up to date, 44 different devices. And the latest one, have been released last year, and every year or so they release new devices. You can have, let's say affordable ones starting from $150 up to, $1,000 for the most, expensive one that contains like barometers and things like that. They all contain a GPS tracker, that allows you to track your GPS coordinate whenever you go for, a run, let's say in the woods and things like that. They have wrist-based, heart rate monitors to, monitor your heart rate, but also, oxygen level in your blood. They can connect to external sensors, so you have running pods that you can, put on around your waist or on your shoes to get some metrics about your running form, such as, balance between left and right foot, stride length, and whatnot. And also a heart rate monitor, strap that you can strap to your chest to have like more accurate readings, let's say during, intensive, workout. In addition to the hardware, they also have, software that comes with it that can provide some, interesting features for folks, such as, a virtual coach. So analyzing your form over, let's say, the past couple of weeks, they can then provide or suggest, workouts for you, whenever you go for a run. You have no idea what you want to do. You start the watch and it tells you something like, go for a 1 hour run at, this pace or, this heart rate, and you can go. And it has built-in applications, but I'll come back to that later. So why are we interested today in Garmin? Well, I mean, if we look at the, smartwatch market, Garmin is actually like second to Apple, at least in 2020. I believe those numbers have changed and now they are behind, Samsung and Huawei. But if we look more specifically in the fitness smartwatch, market, they are one of the major players. The second one would be, for instance, Polar, if you've heard of them. So I think in terms of, potential security impact or, potential user base, it becomes, interesting. And in addition to that, something that I actually didn't know when I started the project, but a colleague of mine let me know, near the end. From 2017, they started to have, news article talking about the U.S. military issuing Garmin devices to their pilots. Apparently, having the altimeter on the watch can help, fighter pilots at high altitude because the reading of the altimeters becomes like difficult on the cockpit or something like that. So we can see references to Garmin Fenix 3 watch, and we can see photos of devices, as well as, a mention to the Garmin D2 model. So that's, let's say, an added benefit if you are interested in looking into the watch. So some recon. Something I found quite surprising, and I think not many companies do that nowadays, is that they actually have a fully custom in-house proprietary operating system. So it's not Linux-based, it's not based on free RTOS or anything like that. It seems to be fully custom, by Garmin. So it has little to no public documentation, at least, when I started the project. And it's mainly written in C with more and more C++ being integrated to handle the UI layer. And these devices support third-party applications. So, like I mentioned, they have a custom MonkeyC language because, if you start custom, why not go all the way? And then when you write this application, you can publish them to the ConnectIQ store, which would be similar to the Play Store for Android, for instance. And it's quite a vibrant ecosystem. I mean, you can find thousands, of application in the ConnectIQ store. Some, let's say, conventional one where you have like watch faces that will just add additional information on the face of the watch, such as, I don't know, if you want to show the weather or something like that. Some like Spotify and Deezer that allow you to stream music from your watch to your earbuds when you go for a run. And also some, funny one. I found one that allows you to improve your barbecuing skills. So, for instance, it lets you know with some timer when you should flip your burgers or something like that. So, it's quite a vibrant ecosystem. In terms of prior research, this is really what kickstarted the whole journey for me. A blog post from, John from Atreides back in 2020. I found it actually early last year, and they, started having a look in the whole virtual machine MonkeyC related stuff, on the device, and they focused on the MonkeyC operation code from the virtual machine and found several vulnerabilities affecting the opcodes. An example, for instance, for the new A, the first opcode, the new array. What they found is that you could request an allocation of, let's say, an array of, 10,000 elements. And during the computation of the backing buffer, you would have an overflow that would occur, and then it would only allocate, let's say, an array of 10 elements. And you can use that to, read out of bound of the array or write out of bound of the array on the heap. And this really piqued my interest because, first of all, it was super interesting, lots of technical details, but at the same time, it was kind of a teaser because there were so many areas, it kind of opening the, Pandora's box, and you got intrigued of, okay, so you looked at this, but then, what about all the loading, of the CIQ application that are also known as PRG files? Because all of that would be, handled by C, potentially memory insecure language, right? There's also a whole permission mechanism for the, watch, similar to what you would have with Android applications. So how are the permissions, implemented? And there is also a mention to native functions. In short, Garmin provide the SDK, and most of it is implemented in MonkeyC. But for some of the function related, let's say, to cryptographic or, graphics operation or Bluetooth connection, those would be actually implemented in, in C. So that would be interesting to understand how wide the attack surface is and how many vulnerabilities you could try to find, and if it can allow you to compromise the device. If you have a look at the, attack surface, very generic. You have the GPS that you could consider an entry point. Bluetooth connection between the watch and the, smartphone. The same connection can be also used for connecting with, external sensors. They also support ANT and ANT+ protocol, a kind of, short range, wireless protocol to connect also to the sensors. They also have a USB stack. You can plug in the device, to your computer to gain access to some kind of file system. The applications, which will be the focus for today's presentation, and for some models, they also have a Wi-Fi stack, so you could consider that also as an entry point. If we have a closer look at the app themselves, there's a lot going on there. You could consider the whole section parsing. So PRG files are composed of several sections, code section, data section, entry point, resources, and whatnot. So any kind of, potential memory-related vulnerabilities could be interesting there. If they don't correctly compute, offsets when trying to parse the, the section, that could allow you potentially to compromise the device. There's a whole signature validation as well. So every application is actually signed, and the watch will refuse to load any unsigned application. So that could be, an area that you want to focus on to try to see if there is any way to, bypass signature validation, basically. Resource parsing. Application can embed, binary resources. So images, animations, fonts, JSON also, data, and so on. So those would be, they are often prone to errors, especially when it comes to a C code base. the whole permission mechanism, how it's implemented. The app storage application can have their own dedicated storage to store, let's say, user preferences for the application. So is there any way from one application to access data from another application, for instance, or any way from the app storage to compromise the underlying operating system? And then, the MonkeyC aspect related to opcodes and virtualization and the SDK function. So, MonkeyC. So this is the mascot. MonkeyC, it's a high-level language that they, developed from scratch. It's a mix between, Java, JavaScript, Python. So if you're familiar with the language, you can really pick it up fairly quickly. Again, developed from scratch. And all of that is compiled to a bytecode stream that is then get interpreted by a virtual machine on the operating system. So an example. This is like the out-of-the-box Hello World, application that you can generate via the, Visual Studio Code plugin. And what this application does is simply showing the time on the, watch, face of the watch. So you can see fairly, common elements such as import statements, defining a class line 6, inheritance, extending a parent class, function calls, function definition line 8 and function calls line 9, variable definition line 20 and so on. So I would say fairly easy to pick it up. And if you compile that, application and run it on the simulator, you would just, show the time on the screen. And how it goes is they have a MonkeyC Java tool in the SDK that will just take that MonkeyC code and then compile it to the bytecode, and that will create and generate the PRG file. So it will take the bytecode, but then it will also create the appropriate data section, the entry points, a link table, and the resources. And since it's implemented in Java, you can just use, JDGUI, open it up. It's not obfuscated in any way. So fairly easy to just gain an understanding of what's happening on the client side, at least. With that information, it really helps you, even prior to looking at the firmware, right? It really helps you to kind of know what you are looking for. Because if you gain an understanding of, the file format that is going to be generated client side, you can then look for, common, let's say, strings or, magic bytes, on the firmware to find location where those data, that data is being processed. So that MonkeyC tool will just, take your application, then compile it to, the equivalent, assembly for MonkeyC. So, like for instance, symbol push and get module and so on. And then take that, bytecode, inject it into the section code of your PRG file and have, additional section around it. So, like you can see on the screen, the first one being the section head contains some, metadata information about your application, version, name, what type of application it is and so on, entry points, data, and so on and so on. Now, moving to firmware analysis. When I started the project, what was very convenient is that Garmin provides you better firmware for most of the devices. So I could go ahead and just download the latest, beta firmware for my device. That firmware, file is a GCD file format, kind of a archive-like format that has already been documented previously by some folks smarter than me. And you can, use their work to actually parse the GCD file format and extract the actual firmware image inside it. The file format supports encryption, meaning a 1-byte XOR key, and this doesn't seem to be used anymore. I guess they assume that people could break a 1-byte XOR key. If you extract the firmware image from the GCD file, you can see that it's a raw image firmware. What's nice is if you look at the entropy, it doesn't seem to be compressed, it doesn't seem to be encrypted. You can actually directly load that file in Ghidra or IDA and start reversing. When I looked at other firmwares, I noticed that for newer devices, at least devices from 2021 and also from 2022, the entropy, I don't know if you can notice a difference. The entropy is slightly different. So it seems that the newer devices have their firmware encrypted. What I'm assuming is happening is that with their newer hardware, they can just provision encryption key during manufacturing, and then they can actually properly encrypt the firmware that will be decrypted when being flashed to the device. But hopefully not the case for my device, so I don't really care. A reverse tip that I learned along the way from Milvich, a colleague of mine. When you are dealing with any device that have a wireless connection, you need to be assigned a FCC ID, and based on that FCC ID, you can actually find a lot of information online. So I was interested in trying to find a teardown of the device, mainly because I wasn't sure what kind of CPU it was running. And I didn't want to damage mine because, most likely I would lose waterproofing if I tried to pry it open. So for instance, if we use the FCC ID from the watch, and try to find, information online, you can find, the, teardown of the device. So you can see the actual PCB of the, Forerunner 245 model. It's not, unfortunate for us, is that the one we seem to be interested in is the shiny one that we can't actually read. But, still a tip to remember for future projects. So at that point, I just assumed it was running similar to the previous model from Atreides blog post. So, a Cortex M3. And actually, if you look at the strings from, the firmware image, you can actually see it's an NXP Kinetis K8 MCU family type of, MCU. When loading it in Ghidra, I was a bit surprised initially, because most of the code made sense, when you loaded it. But actually, as soon as you had like a switch case statement or, some, stub calls, in thumb mode, it started making no sense. And I was a bit confused at first until I realized there is actually an offset difference. And if you look at the address from the switch case statement, you realize that if you offset them by X3000, it actually makes much more sense. And I think the reason for that is most likely that they have the bootloader located between offset 0 and 3000, and then the firmware starting at 3000. So that's why you have to rebase the firmware to actually have a fully, working code. Starting at that point, it's just the grunt work, leveraging the information you gain from, the reversing on the client side, trying to cross-reference that, on the firmware, and then trying to find vulnerabilities. I mainly focus on static analysis. So, in terms of testing, it is, quite slow in a way, because, I couldn't get, like, for instance, a debug interface on the watch. So it took a while, but it's still interesting nonetheless. So now I'll just show a few examples, of vulnerabilities, just to showcase, what kind of things you can find in the operating system. But first, let me talk about a great open source project, KaiTai. If you're not familiar with KaiTai, it basically allows you to define file format using a YAML structure. And with that YAML, it's fairly easy to describe your file format. So you can say that, my file starts with a 2-byte header and then, with a 4-byte whatever, and it's little Indian and big Indian and so on. So I reversing the Java, I just wrote a KaiTai structure for parsing CIQ application that is available on our GitHub. And it can allow you then to compile a deserializer in, various languages. C, C#, Python, whatever. The one main liking feature is that you cannot serialize the data back. I think it's a work in progress. As far as I know, it hasn't been completed yet. And what's great with KaiTai is that it comes with a web IDE that is interactive. It has, a XView and the object tree that is synchronized between the two. So you can actually, in live, do modification of your file formats, and see if it makes sense and then jump around. So if you were to, click on a value and see that, the decoded, little Indian value didn't make sense, you could then just quickly change it to a big Indian, see the refresh results and say, okay, this makes more sense. If you see that the value is in fact 2 bytes instead of 1, you could also make those changes. In this project, to be fair, it's not actually that useful since we have the Java code, so we actually already know how it works. But if you're in a black box perspective, using the web IDE is quite useful. So going back to one of the first questions I asked regarding how app files were loaded. Initially, when I started to look, at the section parsing, I was a bit disappointed to see that most of the offset in the file format were actually encoded using 2 bytes, but they were doing computation using 4 bytes integers on the firmware, which eliminated a wide range of, potential integer overflow vulnerabilities that could occur. But fortunately, there were other areas that were interesting to look at. For instance, resources. So like I mentioned, resources, you can have strings, images, animations, fonts, JSON, and all of that gets compiled into your PRG file. It gets compiled with, an added header that contains some, metadata information about your resource. So it could be, offset and so on. And then it's available at runtime, if you call the load resource function. So for instance, I added a custom font to my application, and then at load time, I can just call the load resource, to get a reference to my, font, and then I can just change the font on the watch face. So if we have a closer look at the string resources, which I think is, the simplest resource that they have, it starts with a 1 byte, sentinel value of 1, followed by 2 bytes, defining the length, and followed by the actual, byte of the string. In the initial disclosure, Atreides mentioned, that there was, a buffer overflow in the new string operator, operation code, that was fixed, in the firmware. I could confirm that. So kudos to Garmin to actually fix it. But then if we have a closer look, I think there was something that, was interesting to note. So when you call the new string operation code, you actually pass a virtual pointer to your resource. That virtual pointer is then converted to a physical pointer, which is more of an offset, actually, than a pointer. And then the virtual machine will read from that pointer to pass the string resource. If we look at the pointer conversion, there are different, type of pointer. So if your virtual pointer starts with the most significant byte of 0, it will actually point to an offset in your PRG data section. If it starts with the most significant byte of 10, it will be in your PRG data section, 20 for your API data section, 30 to your API code section. And during that conversion from virtual to physical, offset, there is actually, boundary checks. So let's say, for instance, you have a virtual pointer that is 0010,000. 00 means that it should point within your PRG data section. But then your data section is only 1,000 bytes long. The conversion will detect that it goes beyond the end of the section and just bail out. Unfortunately, what they didn't consider for loading string is that if we, let's say, take our section start, section end, we have some data there, and then we place our string definition to the very near end of our section, we'll notice that the beginning, like the virtual pointer converted to the physical pointer, will actually point within the section. However, when then reading the, the size of the string, that is in this case, cafe, it will attempt to read cafe bytes, and it will go beyond, the end of the section. So you actually have, out of bound reads when trying to load resources, string resources that are placed near the end of sections. In truth, it's not that interesting because, since we're dealing with strings, it will actually stop copying after the first null byte, and there are quite a lot of null bytes in memory. But it still, I think, highlights some of the weaknesses in the implementation. If we move to font resources, so there are two kinds of font resources. They have non-Unicode and Unicode font resources. Actually, if you were to compile an application nowadays, the compiler will never generate a non-Unicode font resource, but the firmware still supports both formats. So I think for retrocompatibility reasons. In this example, I'm taking the non-Unicode font format, mainly because it's just simpler, less attributes. And you can see, it defines sentinel height, glyph counts, minimum height, data size, and so on and so on. So then when you try to parse the font resource, you'll see that we first, line 1, read the glyph count from the table, then the data size. On line 3, we actually compute the size of the backing buffer that we need to allocate before copying the data. On line 4, we actually allocate it. And then on line 7 and forward, and onward, we actually have a for loop that will copy the data to that, backing buffer. I think you've already spotted, quite an issue in there is that if you select, let's say, a glyph count of 4501A, a data size of 108, the computed size will actually overflow on 32 bits. So if we actually look at the first 8 bytes, the most significant byte of 1 will be dropped, and we'll end up allocating an array of 1A4. And then during the for loop count, we'll actually attempt to iterate over, 4501A, to copy the data to that buffer. So you can imagine it is a tiny bit larger than 1A4. The problem with this type of vulnerabilities in embedded system, it's, they can be quite tricky to exploit. You have very limited, memory available. So in those kind of vulnerabilities, you are
almost certain to hit the end, of the RAM or whatever, and it will just reset the device. So in order to exploit those type of vulnerability, you most likely will need a way to stop the copying, stop the for loop somehow, some interrupt or something. I'm actually, in that case, I'm not entirely sure you can achieve that. And this, type of integer overflow is quite common. You can find them when parsing Unicode fonts. You can find them when parsing bitmaps. You can find them when parsing animations. So you can see it's could be improved. Let's say that. Moving on to permissions. So a quick overview of Garmin's permission. Some modules are considered to be let's say restricted. Those modules can provide you some valuable, information about either the user or the location. So let's say if I were to use the position module, I could retrieve the GPS coordinate of the user. If I have access to the user profile, I can gain access to personal information about the user, their height, weight, and so on. And so for that, Garmin implemented a permission system where you have to, when you compile the application, you have to specify which module you need access to. So it's a static, permission mechanism. And when you do that, you have your XML manifest. You'll say that you need access to the user profile module. Then during the compilation process, they will resolve it to their module ID. And then they will put that inside the permission section that will be checked at runtime. This is an example of permission section for an application. I just specify in my permission, in my, manifest that I need access. In this case, I think it's a user profile module. And you can see the, the ID, the 83012, being added to the permission list. Before understanding how the permissions are actually checked, let's talk a bit of symbol resolution. So whenever you want to call a function in Garmin, in MonkeyC, what happens is that you first push the symbol of the module you want to use. So in that case, I'm pushing the symbol for the toy box communication. In the actual, assembly, it will be the, 0x83012 that I push, on the stack. Then you call the get module that gets a reference to the module. It will trigger the parsing of the class definition that is stored in the data section of the SDK in the firmware. And among the information, it has a flag, for instance, that specifies whether it needs permission or not. Then you will push the symbol for the open web page, the attribute you want to access to, and then call the get value. And the get value will then, parse the field definitions of the module that you just referenced until it finds one that matches the symbol you specify. So at that point, you have a reference to the field definition of the open web page. And finally, you call invoke, which will invoke, the function by taking the virtual pointer, converting to the physical pointer, and then redirecting the execution there. I'm kind of simplifying the, the flow. I'm skipping a few steps, but that's the general gist of it. So a closer look at the class and field definition, just to give you some, information about them. So this is the class definition of my application, of the module of my application. The module ID I have been assigned is 6. Then there is a field value. If you followed along, it starts with 0x10, so it points to the PRG code section. We have the symbol value. In this case, it actually refers to the init that will be used if you want to access that field. It has a value type. MonkeyC defines 21 different types, ranging from integers, array, float, long, and also a method for number 6. And finally, we also have the permission required. Since it's my application, the permission required for my module is not set. So I don't need permission to use my own module. So now, when are the permission checked? Well, actually, whenever you call get module, get value, or put value, you will trigger a check for the permissions. So when get module will pass the class definition and notice that you have that flag set for permission, that it requires permission, then it will actually go through the list of permission in your PRG file. And if there is a match between the module ID you're trying to access and the module ID you specify in your section, it will allow you to go through. And if, there is no match, it will deny you access. The first, kind of silly thing that you can find in that check is that there is an early, edge case that is being handled by the firmware. It seems that if you're running, a version prior to 2.3.0, you can actually use the sensor history without any permission. I most likely assume that this is for retrocompatibility reason. I wouldn't be surprised if that module was released without permission initially and then, it got changed. And that context version actually comes from the head section of our PRG file. So what we can simply do is that we can tamper with our PRG application, that head section, specify that we are running actually version 2.0, and then we gain access to that module without having to specify it in our permission list. But there is something more. And I think let's go back to the symbol resolution. I think fundamentally there is something that really bothered me when I looked at the steps, is that I find it odd that the permission check is not actually on the invoke, and that the permission check occurs prior to the invoke. So the question is there a way to invoke a function, and bypass the permission? And actually there is. If we go to our class definition and our field value, so again, 10, most significant byte starting with 10. So it points to our PRG code section. What we can simply do is update it to another value. And in this case, the value I specify is the pointer, the virtual pointer of the open web page function that, I mentioned prior. And what happens is that when you call that function, when you call the get module or the get value, the flag that we will check is the flag of the module that you have just defined, and the flag is set to false. And so you can effectively bypass any kind of permission in the Garmin, MonkeyC virtual machine. This is the simplest case, meaning that I just redirected one function. But you can go further. You can actually take the whole SDK, embed it in your PRG file. You have to clear all the permission flag and then, fix all the relocation offset. And then you can call arbitrary modules and arbitrary functions in your PRG application without defining any permission in your list. So you effectively completely bypass the permission mechanism implemented by Garmin. Last question I was asking about, native functions. So the SDK is mainly implemented in MonkeyC, but there are many functions that are actually implemented in C. So for instance, functions related to graphics, and plus, Bluetooth, HTTP, encryption, storage, and others. They are all implemented in native code. And what that means is that, if one of those functions has a vulnerability in it, you could potentially leverage that vulnerability to compromise the system. And when I looked at the firmware, they had over 460 native functions in there. That's quite a lot. I think in terms of attack surface, you have quite a large playground to play with. So you can see on the list of the symbols resolved, you have the burst payload, add, get size, next, get device config, all of that. So any one of them being vulnerable, could be exploited. So let's go for a few examples. I'll give you just a few seconds to get familiar with the code. So what we have in this function, the cipher initialize. It allows you to initialize the context prior to encryption. So you can specify which cipher you want. You can specify your encryption key, your IV, and then you have another function you can call to do the encryption. So if we follow along on line 12, we basically check which cipher we are requesting. So if we are requesting AS128, the expected key size is 16 bytes. If we are specifying a cipher or 256, the expected key size is 32 bytes. And then on line 18, there is a check that ensures that the key data length is, the expected key size. And if it is different, then it will bail out. But actually, line 10, I just hit something. Line 10, they actually do the mem copy prior to checking the size. So what they're effectively doing is that you can provide, let's say, a key that is 200 bytes. They will call memcopy, then they will check the size, and they will bail out. So, except that line 22, when you bail out, you already compromise, or you already overrode the full stack. So you have control over the return address, and you can hijack execution. Second example. This is a 2-for-1. I'll give you just a second. So this is the burst payload add function. What it does, I'm not entirely sure, to be honest, but you pass it an array of 8 bytes, and it will store it in an internal buffer. And to do that, that internal buffer is limited in memory. So if you try to write past x2000, it will return an error, an out-of-memory error. But if you have enough space, it will simply copy the data to that buffer. So first issue, line 5. The comparison is signed. What does it mean? Is that although you have an upper bound, you can actually provide a negative size and write prior to your backing buffer. But more than that, let's assume for a second that line 5 is safe. Let's assume for a second that they do check for, a lower bound. Then we have another issue. Is that line 12 and 13? Are we sure that this is the object we expect? Well, it could be different. We have the capacity to actually change the object to something else. So instead of being that backing buffer, we can say that it's an integer, or it's a string, or it's an array of, some random object. So first example, how do we control those attributes? Well, we can benefit from inheriting from the object. So we create our own class that inherits from the burst payload. We call its initialize function to do the proper thing, and after that we override the size field to point to a negative value. So in that case, deadbeef. Then we create the data, the 8 byte of data that we want to, add to the buffer, and we call the add function. And then, whenever we'll reach, the line 12 and 13, the size will be actually pointing prior to the beginning of the buffer, and you can overwrite arbitrary location on the memory, from a relative position. The second example, as mentioned, is very similar process. So you inherit from the burst payload, called the initialize function, and then you override the burst data blob to become an array of 2 integers. The data then you try to add, you carefully craft it in a way to actually become other type of objects. And then by calling the add function, again, I'm going back, to the vulnerable code. By calling the add function on line 12 and 13, you will actually override those objects in memory. So you can effectively convert, in that case, integers object to float object. But you could obviously use different type of object. You could convert from integers to strings. You could convert to overwrite the size attribute of an array in memory. So your array that is initially 10 elements, you can then overwrite its size attribute and say that it's actually 1,000 elements, and then read out of bound or write out of bound. I have to admit that exploiting those vulnerabilities are not easy. Surprisingly, Garmin has full ASLR. They have stack canaries. What do they have? They have a sign pointer. I'm just kidding. They have none of that. It's back to the 90s. You can just override the stack. There's nothing there, and you can just hijack the execution. So in this demo I'm presenting today, if you remember initially, some devices now have encrypted firmware, and this is one I have here. So this is the model 55. And the idea was trying to develop an exploit for one of the vulnerability ported to that device to be able to exfiltrate the data. So if you can switch over, I'm going to give it a try. It's a bit tricky because I'm upside down, so you have to excuse me. So what I have in my hands is just an Android phone, which is paired to the device. And on there I have running just a listener to listen for the data. Then on the watch, I can simply start an application. So we're not going to run today, maybe tomorrow. We're going to start our own application. So what that application is doing is that in memory, I have placed a byte array object. And then I'm going to exploit the initialize vulnerability that we mentioned earlier. And the goal is for that vulnerability is to hijack execution, find our byte array in memory, overwrite its content with the content of the firmware image, and then exfiltrate that through a HTTP request. So if everything goes right, I'm going to mess it up, I'm sure. So you have on screen the first 1000 X bytes of the firmware. And we can actually go over manually and go over the range of the memory.
And in the meantime, in the backend, what I'm doing is that I'm sharing that data to my phone via HTTP request so that I don't have to type all of that by hand. And store it in a SQL-like database so that I can just manually reconstruct the data, offline. And by doing so, I can simply retrieve, the device. So what we have is that we started from, an encrypted firmware, this, model 55, like I mentioned. And through the, exploit, we can actually, exfiltrate the data, to our, Android application. Why HTTP and not something else? It's a bit tricky to store large data on the device. If you try to log it, the logs get cleared after 4 kilobytes. If you try to store it in the local storage, they don't really like storing large values, so it will simply fail. So I just use HTTP requests. Obviously, I was doing it manually by hand, every 1,000 by 1,000, but you can actually automate the process to do that. And by doing so, you can actually exfiltrate, part of the firmware. In that case, I'm just exfiltrating from offset 0 to I forgot which value. That would refer to, the code section, basically. And then you can load it up in, Ghidra or IDA, and you have the firmware. So let's go over some conclusion. So performing an analysis of the Garmin Forerunner 245 music started last year. Again, focusing on its virtual machine, trying to go a bit further than what was already done when it came to applications. In total, we reported 14 vulnerabilities to Garmin. One of them allowed a full bypass of permissionless system. Several of them allow full control of the execution of the firmware. And going back and forth with them, trying to understand which model were actually affected, because, looking at some of the firmware, I could find the same vulnerable code, across multiple devices. And they got back to us with a list of more than 100 affected devices. So apparently those devices include, fitness watch, outdoor handhelds, and GPS for bikes. And some of the vulnerabilities, such as the permission bypass, has been there since the very first version of the CIQ SDK, so published in 2015. What's a bit surprising when communicating with them, and I'm not entirely sure I fully understood what they explain, is that they don't seem to support the devices that are old, and by old I mean 2 or 3 years old. So it seems that a lot of those 100 plus devices are still vulnerable despite the patch being released. For this research, we are going to publish a GitHub repo that contains the various information I shared here. That would be the character structure file for parsing CIQ application, a Python script leveraging that character structure to allow you to tamper and modify your PRG application. So you can more easily, let's say, tamper with the opcodes in the code section, or tamper with your resource structure, and then regenerate the signature automatically for that. There is also, a folder with proof of concept applications for most of the vulnerabilities, and then the demo I just showed leveraging the vulnerability in the Cypher initial hash function. In terms of coordinated disclosure with them, we started back in July last year. And after a few back and forth, they first initially said that December 3rd would be a great deadline. And then finally February 20th. And then finally they changed again and said March 14th. When we pinged them on March 14th, they actually said that they released most of it, but there are still a few devices that are yet to be patched, and they are aiming for March 22nd. And I hope that by then they did it. I didn't ping them again. For some future research areas, in case anyone is interested, either to do it yourself, or if you want to collaborate, that'd be great. I mean, if you've noticed, I barely scratched the surface of the Garmin operating system. I mean, I really looked at a tiny part of the virtualization for the PRG application, parsing of PRG files and so on. But we haven't looked at the ANTs or BLE or Wi-Fi or GPS stack. We haven't looked at the USB stack. One thing, I was curious about is the notification system. If you are paired with your phone, if you have a notification on the phone, it gets shown on the watch. And they do Unicode conversion, between Unicode and UTF-8. So it'd be interesting to know if there is any bug in there that could allow you from one notification to compromise the watch. That'd be fun. And also the signature validation. So why didn't I look to the signature validation? Well, I mean, to be fair, mainly because on the watch itself, you have no option to disable developer signature. So what that means is that if you are not signed from the CIQ store, you can just sign it yourself with your own developer's, signature, and then it gets accepted by the watch. So at that point, I didn't really feel like it was needed to bypass the signature, since you could simply use the developer signature. And there is no, information, notification, or warning that, this app is, signed by a developer signature, and there is no option to disable that option. So, yeah, it felt like it wasn't necessary at the time. Also, I heavily focus on static analysis. So mainly because that's what I enjoy the most, but also because I'm really bad at anything related to fuzzing. So if anyone is interested, have a look. It could be through some hardware setup, looking at some maybe, debug probe, connection points on the PCB. I know actually mentioned a QEMU patch to try to run the firmware, but they didn't release anything, and I don't know what, in which state it is, but that could be, an alternative. And as you can see, through just simple static analysis, some very obvious bug. And I'm sure that if you run any further in there, it will just blow up. And finally, some debugging would be great. Developing an exploit when you don't have a debugging environment on embedded devices, quite a pain. So that's it for me. If you have any question.
Thank you, David. Any questions in the room? Yeah, you are.
You mentioned that the Garmin does not accept any application that is not signed by Garmin. How does that work if you're developing apps? There's some sort of bypass for that?
So I didn't say they are not loading applications that are signed by Garmin. I just said they don't load applications that are not signed. And that signature can either be Garmin signature from the Connect IQ store or your own developer signature.
Okay, but then you need some sort of developer certificate.
That you can generate locally. Similar for Android application, for instance. You have your own signature, your own key generated locally that you can use to sign your debug builds.
All right. Thank you.
Welcome.
Any more questions? Yes, one more in the back.
You said the new firmware is encrypted. Did you, were you able to extract the encryption key?
No, I haven't had time, to be honest. I think I extracted, the firmware, something like last week. But this is something I'd be interested to look at. It was actually the whole idea behind trying to port the exploit to newer models, is to have a look at how they are doing encryption. Is it, let's say, the same key for all the models? Where the key is stored? How is this going on? But yeah, I'd be interested to look into that.
Okay, thanks.
More questions?
So one quick question. If you're wondering, are those military devices vulnerable? The answer is yes.
Yeah. Okay, thank you.